Okay, so let us start with the next subtopic of this chapter. So that will be on homogeneous equations. Okay, so as the name suggests, homogeneous, the name equations. Okay, homogeneous equation. Okay, now just understanding here, the word homo means same, right? Comes from the Greek alphabets, Greek language. Okay, so homo refers to the same, and genus means the type. Okay, so here we are kind of saying that it's a function of the same type. Okay, we'll be again meeting this homogeneous somewhere later on up. Okay, somewhere towards the end of this chapter, there homogeneous will have a different meaning. Okay, so that's kind of a little bit confusing thing, but actually when we are talking here now, we actually refer to the function as homogeneous. That book is not born like that, so I won't do it. Okay, later on there it means something else, completely differently. Okay, why that has happened is, according to the book, many people across the world were studying the same topic at the same time, or rather studying different topics at the same time. So they gave the same name to different things. Okay, so, and that thing remained like that only, nobody had to change anything. Okay, so now first let us define what we mean by a homogeneous function as such. Okay, okay, so definition. Okay, definition, a function g of xy, two variables, okay, function of two variables means it's dependent on two variables, okay, x and y. Okay, not your regular functions which have only one dependent variable, one independent variable. This one is two independent variables. Okay. Okay. So g of x of variables x and y. You can sit behind also. No, if fellow okay, then sit. Yeah, then sit behind. Okay, function g of x of variables x and y, okay, is said to be homogeneous. Okay, homogeneous of degree alpha, where alpha belongs to the set of real numbers. Okay, alpha is a real number. Don't know that this notation is for set of reals. Okay. So for real numbers, if g of, what I'm going to do is, instead of writing g of xy, I'll write g of tx ty. Okay, so what I'm doing is I'm multiplying an extra factor over here. We'll call it a parameter. Okay, so we'll multiply that extra factor as such into x and y, and then we'll operate it on the function. So what we'll get here resulting is, the function which you get, you can take this t out common. Okay, t comes out common with some degree alpha. Okay, and this becomes the original function x comma y. Okay, so in other words, you can take some factor outside of the equation or outside the function. That's what it means. Okay, for all t, For all means any t greater than 0. If you take negative, obviously it will not work, because it may not work because negative sign creates a problem with degrees. Okay, when you take negative to the power something, it changes. Okay, so that's why we are not interested in negative over here. We'll just focus on the positive things. Okay, so let us see some examples here and then you'll understand this better. Examples. Okay, here we'll take it as first one. G of xy is given as x square plus y square. Okay, so let us see if this thing works. So instead of x and y, I'll write tx and ty. Okay, so here I have x square plus y square, so this should become tx the whole square plus ty the whole square. Okay, clear? So now what do you see here? That this t square will come out now, right? And this is nothing but t square into g of xy. Okay, so what we'll say? So hence G is homogeneous of degree. Okay, G is homogeneous function of degree 2. Next, let us take this example. G of xy is going to be equal to, just keep in mind that t which I was using here was greater than 0. Okay, xy upon x square plus y square. Okay, so same thing we'll do. We'll take here g of tx, ty. Okay, where t is strictly greater than 0. Okay, this will become what? This again is defined when x and y is not equal to 0. If x and y are both 0, then the denominator becomes a problem. So we'll put a condition there that x and y at the same time should not be 0, 0. Okay, one can be 0, another one can be non-zero, that is allowed. But both of them should not be 0 at the same time. Yeah, so what will be tx, ty? This will give you tx into ty upon tx the whole square plus ty the whole square. So as you can see, the top thing will give you t square over there common, xy. Denominator also leaves you with a t square, right? So this is nothing but t square will cancel, because t is greater than 0, we can cancel it out. Okay, so xy upon x square plus y square. Okay, so xy, x square plus y square. Yeah, and this is your g of x. Okay, so now there is no t coming out here as such, right? It actually became t raised to 0, right? It's become 1 times this thing, so 1 can be thought of t raised to 0. So here again your function is g is homogeneous of degree 0. Okay. Third one, g of xy sine of x into cos of y. Sine of x into cos of y. So what will be g of p px? This will become sine of px cos of py. Can you take out the t now? No, right? The t does not come out of the sine function like that. Okay? So this cannot be simplified as t times g of xy. Anyways, right? So what's going to be a conclusion here is g is not homogeneous. Not homogeneous. Actually, the majority of the non-homogeneous functions which we'll be dealing with now will be this people only, sine, cos, and e raised to something. Right? These people are not homogeneous anyways. Okay? So moment they come into the picture, they are obviously a function is not going to be homogeneous. Okay? So yeah, if these people come into the function, then your function is surely not homogeneous. But they can be other ones also, even though that these people are not there, the function is not homogeneous. Let us take for example this one. G of xy is going to be equal to x cube plus y square, where this much is over. Okay. So now what will be g of px py? This will become px the whole cube plus ty this is square. So t comes out common here. So t square will come out common. 1t will remain here. Okay. So is this in the required form we want? No, right? This t remained back over here, right? So that is not good for us. So G is not homogeneous. Last one. Let g of xy will be equal to root over what will be your g of px px py, this will become 1 upon root over px the whole square plus py the whole square. So p equals e square will come out common. So e taking out of the root sign, what will be left out is 1 upon t root over this. So this is 1 upon t times g of xy. Okay. So hence G is homogeneous of degree homogeneous of degree minus 1. Okay, because this becomes t raised to minus 1 actually. Okay, once you take it on top. Okay, so these are the examples which we have to see. So now let us go ahead to solve our differential equations. Okay, so method to solve homogeneous differential equations. Homogeneous, right? Homogeneous. Equations. Homogeneous differential equations. Okay, so consider the differential equation equation given as mxy dx plus mxy y equal to 0. Okay, so what I have done basically, you all have studied the differential equation as dy by dx is equal to f of xy, right? So I have kind of separated the functions over here. Okay, so I have taken one of them with dx and one of them with dy. What do I mean by one of them? Okay, when I do examples, I will understand that how this thing became this one. I'll explain it with the examples after some time. This is how your differential equation should look like. I can convert it to this form, okay, by just rearranging the terms basically. So, uh, consider differential equation given as mxy dx and nxy dy equal to 0, where mxy and nxy have the same degree of homogeneity. Okay, basically, in other words, m and n are homogeneous functions of the same degree. Okay, that's what it means. Okay, same degree of homogeneity means both of them are functions of the are homogeneous functions of the same degree. Okay. Yeah. Then we perform the change of variable, where z is equal to y by x. Okay, to make the equation variable separable. Okay. Make the equation variable separately. So let us see examples now. We perform perform okay, we perform the change of variable z is equal to y by x and make the equation variable separate. Yeah. So let us see some solved examples here. Exercises. I'm solving for the exercises here. I'll give you the soft copy of the book today on the classroom. I'll upload, but that book has different numbers from this book. Question numbers are a little different. That's a different edition, in fact. Okay. So anyways, I'll write the full question again. So x minus y dx minus x plus y dy is equal to 0. So this is the given question to you. Okay. So the first question over here is, can you solve this problem using the previous method which we did? Previous method we have studied only one so far, so that is variable separable. So can you make this equation variable separable? No, right? So anyways, if you try taking that one term on the other side, that x plus y dy, that will go that side, but that y will remain this side and one x also goes that side, right? So this is not variable separable. Okay, so whenever we are solving a differential equation, always be sure that you cannot solve this problem using any of the other methods. Any of the previous methods at least. Okay, so you can solve it using the previous method, or you can use that method only, unless this is some way superior method or something like that, as we'll see somewhere later on. Okay, so the first thing we have verified is that we cannot solve this problem by variable separable. This function is not variable separable, that we can see. Okay, next is verifying the degree of homogeneity over here. So what is your mxy? That is your x minus y, and what is your nxy? This is going to become equal to 8x plus y. Is this function homogeneous? You can do it in roughly. What will happen if you try to replace tx, x with tx and y with ty? You get tx minus ty. T will come out common. So this is homogeneous of degree 1. Degree 1. What about the second one? Same thing, no? This is also homogeneous of degree 1. Okay, so both the terms m and n are homogeneous of degree of the same degree, right? So what we'll do, we'll replace, let z is equal to y by x. Okay, so now how this method works is the main working of this method. So z is a new variable depending on x as well as y, but it's more important, y depends on x, by the way, because y is a dependent variable for our problem, right? And x is independent, so z also depends on x, because z is a function of y by x, so x is the inverse, right? This is the thing. So you write xz is equal to y. So now apply derivative on both sides, taking derivative. So what you'll get? You'll get z plus x times, when you take the derivative, this is a product rule involved here. Okay, x and z. Z is a function of x indirectly. Okay, so z will remain as it is, x will become 1. So plus x will remain as it is, and then you'll have to multiply it with dz by dx. Okay, next over here you have y, so that is y is a function of x, so that will become dy by dx. Clear? What I've done? Okay. So use product rule on one side and I got this. So now the given differential equation is given dE is x minus y x plus y dy equal to 0. So first we'll write it in the form dy by dx, taking this that side. Right? Okay, so by rearranging the terms, this is what I get. I took this on the other side and then I brought the denominator back and took dx down. Okay, if you want, I can show that step. So this is what we get. Next, I want to convert it in that form, right? So what I'll do, I want it in the form y by x. So what I'll do, I'll divide numerator and denominator here by y by x. Divide numerator and denominator by x. So this will become 1 minus y by x. This will be 1 plus y by x. Okay, so dy by dx. Okay, so this is the thing. Okay, so now we can perform the substitution. Okay, so I got it in the required form. Now I can perform the substitutions. So yeah, so this is going to be 1 minus z upon 1 plus z, and this is equal to what? So z plus x times dz by dx. Okay. So it's almost become variable separable now. We have to just rearrange some terms. Take z on this side. 1 minus z, 1 plus z, minus z, x plus dz by dx. Okay. So this will become 1 minus z minus z times okay. So 1 minus z minus z square. So here we are now. Just take this thing. It became variable separable now, right? So x goes here, dx comes down. Dx goes on top, x comes down, and this will become 1 plus z on 1 minus z square dz. Okay, so now we have to integrate distance.
So there is minus z.
Yeah.
Minus z minus z.
Here, oh, there is a minus. This is going to become difficult now. Minus 2z minus c square. Oh no, sorry. We'll have to work a little hard to get this integrated now. Okay. So this will become 1 minus okay, so RHS this side it's very clear what is going to become. This will become log x, sorry, ln of x. It's going to become ln of x plus ln of c. I'll write down directly. Okay. Here there will be a problem for us to fit and integrate this out. 1 minus 2z minus z square dz. Okay, so here we have to deal with something difficult. But it's not so difficult. Right? How will integrate this? One thing about this book I know now, the problems look difficult but the integrals are very easy. This looks like a difficult integral, right? But what's the shortcut over here? You will see in a shortcut. Okay, what is the method you will apply for this particular thing? Particular integration. What is the type at least? Well, have names no for these types. This is something what I will call linear upon quadratic. Okay, first order polynomial upon a second order polynomial is there. So it's linear upon quadratic form, right? What we used to call it. Okay, so this is linear term over a quadratic term. Okay, in other words, you'll have, I think so I've studied it like this: cx plus b upon ax square plus bx. Ax square plus bx plus c. What are the alphabets are there? Ux plus v. Okay, yeah, what will do in this case? I'll do something now. A times d by dx denominator. I'll replace the numerator with a plus d by dx by denominator plus b. Right now? Yeah, try this and see what will happen. Actually, if you can see the answer straight away, it's very clear. What is the numerator here? 1 plus z, right? Is it related to the denominator in any sense? Can you express the numerator as a derivative of the denominator? What's the derivative of the denominator anyways for this problem? What will it be? It will become minus 2 minus 2z. Right? If you take minus 2 common, what will you get? So what can you say? The numerator is actually minus 2 times the derivative of the denominator, right? Basically, if you had worked out this calculation over here, no, you would have got the same thing. A would have come as minus 2 and B would have come as 0. Okay, so you can go home and verify this calculation. Okay, because if you verify it, it will be better. Okay. If you will become experts, that is always better, that if you can look at something and find out the answer, it's very good. If you all can't do this, never mind, try this out. Okay, this is the actual method which is required to solve this. Okay, express the numerator as a times the d by dx, the denominator, plus b. Okay. So now what I will be saying is, so this is integral of minus 2 times d by dx of 1 minus 2z minus z square upon 1 minus 2z minus z square dz. Okay, so what is the integral of this? I'm asking you the integral formula for this thing. 1 upon f prime of x upon f of x. What is the integral of this? Forgot? Revise this and come home. Okay. Anyways, this integral is what? This integral will work out to be equal to, I'll write ln of, let's get used to writing ln of modulus of f of x. Why do I put modulus? Because these functions might become negative somewhere or another. So just to avoid any trouble with regard to that, I'm putting modulus over here. Okay? Because this log functions are defined only for positive values, right? So better this fx remains positive. So I put a modulus, right? Yeah. How do you be sure that what I have written here is correct? If you have ln of f of x without the modulus of it, to take the modulus while doing this part now, it will be a little extra work will get involved. So if you have ln of f of x, what is the derivative of this by chain rule? First you have to take derivative of log. What is derivative of log? 1 upon x. But you don't have x here, you have f of x. So what will it be? 1 over f of x. What you should do next? Take derivative of the inside term. So what is the inside term? F prime f of x is the inside term. Take its derivative, that will give you f prime of x. Right? So d by dx of this gives you f prime of x upon f of x. Alright, so what should be the integral of this? This. Okay? That's one way to prove this particular result. Okay. So hence we have here minus 2 times ln of modulus of 1 minus 2z minus z square. Okay, just keep in mind I'm writing modulus just to avoid the negative values to come inside, because log is defined only for positive. So that's why I'm writing modulus over it. Okay, so this will become ln of x plus ln of c. This will become ln of x into c. Right? So now we require certain extra properties here of log. What are the properties you need? Yeah, the properties of log are what? You know that log ln of x plus ln of y becomes ln of xy. Ln of xy. Next, ln of x raised to n will become what? ln of n times ln of x. So basically that power n which is there, it will come down and it will stay down. Okay, x raised to n will become n times x. So here what we have, here we have minus 2 times this, right? So this should become ln of modulus I'll write here 1 minus 2z minus z square to the power minus 2. Okay, clear? Using this property. By the way, this property follows from here on. It's not. This is the main property of logarithms. This one follows from this. How do you prove it? You take x and x value on both places. So ln of x plus ln of x will be equal to ln of x square. Okay, so this will become 2 times ln of x. Okay, you can repeat this for the next one also. Ln of x plus ln of x plus ln of x plus ln of x. Right, it will become ln of 3 times ln of x is equal to ln of x cube. Okay, so on it will go. So by induction it will become this. But not only for induction, it even works for negative numbers, negative powers. Okay, so this is the thing here. So here you have this is equal to this. You can remove the modulus on both log and the modulus also on both sides. This will leave you with 1 minus 2z minus z square the power minus 2. Okay, what is negative power? Negative power means it's this 1 minus 2z minus z square the whole square. Okay, negative power means take it down. Yeah, so resubstitute now. I'll do the thing here on my page whatever. So you have x times c, 1 upon 1 minus 2 times y by x minus y square by x square. Okay, so this is the final answer, but you can, if I want, you can simplify it further. Right, so you can take that x square out. Common. Okay, you can take this x square out here if you wish to. The problem is over at this stage, so if you are not so good in simplifying terms now, don't proceed beyond this point. Okay, you can stop here, but if you want, you can try it out further. This will become x square minus 2xy, okay, minus y square, the whole thing upon x square. X times c. Okay, so x times c will become x raised to 4 will come on top, and denominator will be left out with x minus 2xy minus y square. The square to the power square will be there. Yeah, you can cancel one x over here and write c is equal to x cube by that time. This is one. Okay, so this is your answer. Okay, so let us go for one more problem here. Okay, so let's go to the next problem. Problem number 2. xy prime is equal to 2x minus 6y. Okay, so this is going to be x dy by dx is there. Okay, so 2x minus 6y. This can be written as x dy minus times 2x minus 6y dx equal to 0. So I took this on the other side and got it this side in one step only. Okay, both the functions here are homogeneous of x and 2x minus 6y. Both of them are homogeneous of degree 1, right? Okay, agreed? Okay, so if you write this as tx, t will come and stand outside there. Here also t will come and stand outside. Okay, so are homogeneous of homogeneous homogeneous of degree 1. So since this is the case, yeah, now we can go back to the original problem. That was y prime y prime is equal to 2x minus 6y. Okay. So this can be easily written as 2 minus 6y by x. Okay, and this side you can write this as dy by dx. Okay. So let y by x be equal to z. So what will get here? This will imply that y is equal to xz. So hence dy by dx is equal to, okay, it's going to be z plus x times dz by dx. Where is the sound coming? Chair is making the sound. Okay, I thought there was a squirrel or something. There's no squirrel behind the curtain or something there, no? Just check. No, no. Sounds like a squirrel actually. Okay. So here we have this. So now hence the given differential equation becomes z x plus dz dx is going to become 2 minus 6z. Okay. By the way, I write 2 like this now, and I write z like this to avoid confusion. I know many people like to write z like this, but after some time they only get confused whether this is a 2 or z. Okay, so I recommend you all also write z like this. Don't use this as z. Unless you are using it for capital Z, and capital Z will become a little clear. Okay. Yeah, if you want to be very specific, write 2 like this, like the Devanagari 2. Okay. So here we are. So this goes this side. So x dz by dx 2 minus 6 minus this z over there. So I write it directly as 7z. Okay. So then just rearrange the terms. dz 2 minus 7z dx by x. Okay, so take log on both sides, integrate it on both sides rather. So this will become ln of 2 minus 7 2 minus 7 z, okay, and ln of modulus of x plus ln of modulus of c also. Okay, so this will become simplified to ln of x by the properties of log which I stated above. Okay. Okay, so taking exponential on both sides, this will become 2 minus 7z minus is equal to x times c. Okay, so what is z? Y by x, right? So this will leave you with 2x minus 7y equal to x squared. Yeah, I replace z with y by x. I'll show the step. 2 minus 7z, right? Yeah, so this will become 2 minus y by x. So this I'll write it as 2x minus 7y by x, right? Okay, and then this x I'll take on top, which will give me the x square value. Okay, so done. We'll go to the next problem. Problem number 3. Yeah, problem 3 over here. So this will become x y prime is equal to root over x square plus y square. So writing this in that form, x dy by dx is equal to root over x square plus y square. So this can be written as x dy minus root over so this is homogeneous of x and root over this thing. You can verify that both are homogeneous of degree 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 homogeneous of degree 1, right? So hence this equation is homogeneous and we can do the required part for us. Hence this is a homogeneous differential equation. D homogeneous differential equation, right? And we have y prime is equal to root over right. This is what we are given, no? So let us just write this like this. Okay, now how can you simplify this expression? I taken the x down there. How will you simplify it? So we'll write the denominator as square root of x square, right? So that will work. Square root of x square, you can just think of this whole thing as square plus y square upon x square. What will this reduce down to? 1 plus y by x, the whole square. It will become y square by x square, but you can write it as y by x the whole square. Okay? Clear? So the same substitution as last time. Put z is equal to y by x. So this will imply xc becomes y. So you get z plus x times dc by dx equal to dy by dx. So substituting in the given differential equation, this will become z Alright, so this is what you get. Let's simplify it now. X dc by dx, this will become z so dz becomes of integration root over 1 plus z square so we have reached here. So how will deal with this situation now? Do you know any particular integration should work here? There are no formulas if the entire denominator was under a square root, but that's not the case here. Only half of it is under the square root and half is outside. So what can we do? How do you deal with square roots and this? Huh? What's the technique to deal with square roots? What I studied in school I'm talking about. Huh? Well, yeah, so we'll rationalize this thing, no? So what is the rationalizing factors involved here? So I'll take 1 plus z square plus z divided with the same thing. So I'm basically multiplying 1 only into my equation, right? Because both these terms anyways cancel. So 1 plus z square minus z. Okay, how do you decide the term for the rationalization? If you have 1 upon a minus b, you take 1 upon a plus b and vice versa, right? Okay, and this is dz is equal to, this will become ln of x plus c. Yeah, so what is the property which we'll use for rationalizing here? A minus b into a plus b, what is this? This becomes a square minus b square, right? Okay, so this is a plus b into a minus b, so a square minus b square. So this This will become, numerator becomes 1. So this will become a square minus b square. So it will become a square minus b square. bz. So denominator is gone away. So we have to integrate only. This should be an integral sign here. If I integrated that other thing. Because I integrated the other sets, so the integral sign had to be written this side also. So we have to integrate only root over 1 plus c square plus c. Okay, so this is what you're going to end up with. So what is the integral of the other fellow then? What's the integral of this other fellow? This is going to be z square by 2 in the second term, and plus integral of this. Right? Do you all have a formula for this? There is a formula for this, right? What is that? This is the This is the one of the 9 standard integrals which will have. This is, I think so, g square by 2 or z by 2 times z plus z by 2 plus ln of, sorry, I will just check this one. Yes, right. Okay, it is actually of the form integral of root over a square plus b square. It comes with the log of n. Root over a square plus x square. Yeah. So this will become half times. It's actually x by 2 root over x square plus a square plus a square by 2 log of x plus this one. Yeah. So this is the integral. The formula for this integral is integral of root over a square plus x square. That integral is, which I'll study it as x by 2 root over a square plus x square plus a square by 2 log of the entire expression. No, sorry, not entire expression. It becomes really x plus root over x square plus a square. Okay, plus c. This is the integral formula. This is a very rare integral formula. I hardly use it, so you don't remember it also. Yeah. So, anyways, the answer to our question will be So this will become z square by 2. In our case, this formula becomes z by 2 root over 1 plus z square plus 1 by 2 ln of, since we are talking only of natural logs here, z plus root over z square plus 1. C I won't write, but C I have written already on the other side. Okay, so and this is going to become ln of x. Yes. Now resubstituting the spelling is wrong. It's y by x the whole square divided by 2, again y by x divided by 2 root over 1 plus half times ln of okay. So this is the thing. I don't see anything big happening once it's simplified. Let us not simplify. It can be simplified a little bit, but I doubt anything good will come out anyways. It'll just be the same thing as like, okay. Anyways, so moving on. Let's go to the another problem. How much time you have? Let's see. Next problem. Problem number 3 or 4 we are doing? Huh? Fourth one. No? X square y prime, okay, is equal to one thing now about homogeneous thing we all will notice is, especially in that definition, all the examples which I gave you all over there, just see the examples, all of these functions now they have the same degree over there, right? What are the examples we have done? The degree of the terms was same, okay, so this is one important observation you can make. See, this was homogeneous, here the degree of the x term is what? X2, y term is also 2. So it's basically the degrees are same. Okay. Now notice in the second example, what's the degree of x here? 1. Y is 1. Okay. So 1 plus 1 will give you 2 because they are multiplied together. Okay. Since they are getting multiplied, the degree of xy term is 2. Okay. What about the denominator term degrees? This is 2. This is 2. This is going to remain separate. Huh? This is addition. No addition. The degrees are not combined. Okay, so denominators of degree 2, numerators of degree 2. Okay. So, hence the thing is, the degree of homogeneity over here is 0. 2 and 2 cancels each other. Here there is no degree term only. Notice here now, for the third of this example here, this is of degree 3, this is of degree 2. Was it homogeneous? No. So if you have different degrees, then it's surely not going to be homogeneous. Huh? Okay. Clear, no? So That's how the name also comes. Homogeneous, we are referring to the same type or same degree over here. Okay, so if the terms are of different degrees, then surely not be homogeneous. Okay, just keep that in mind now. Okay, so this example, notice the terms here. This is of degree 2, this is of degree 2, and this term is also of degree 2. Okay, but just don't believe it blindly. Try to verify all the steps. Okay, so here we have x square dy by dx. So dy, so you'll get x square dy minus, okay, so x square is, and both are homogeneous, right? Well, you can verify this one, both are homogeneous. Okay, so it's homogeneous of degree 2, hence this is the homogeneous equation. Differential equation, that's enough. Okay, so what are we given? We are given that x square y prime is equal to y, y square plus 2xy, right? So this can be written as dy by dx what will this simplify to? This can be written as, separate the denominator, so this can be written as y by x the whole square, and this can be written as 2 times y by x, right? So yeah, let y by x is equal to z, so y is equal to xz, so dy by dx is going to be equal to z plus x times dz by dx. So the given differential equation becomes the given differential equation becomes z plus x dz by dx plus z square plus 2z. Okay. So this will reduce down to x dz by dx. Okay, z square plus z. Okay, z I'll cancel one side. So here I'll write the denominator as, I'll take that z out common first. z into z plus 1, okay, dx by x. Yeah, so now what we'll do, I will integrate both sides. What's the method to deal with the LHS over here? What will you do? What's the method to integrate this? Forgot or what? Huh? Going to integration by parts for this? When did you apply integration by parts? When you have a product of two functions, right? That is okay. Here you have product of two functions. I can see that. Okay, what are the two functions? 1 upon z into 1 upon z plus 1. Alright. So now, is only two functions the only required thing for integration by parts? One of those two functions which are involved in integration of by parts, you should be able to kill that function, no? The derivative of that function which you are doing integration by parts with, one of them derivative should become 0 or constant after some time. Okay? Otherwise what will happen, that integration by parts method will never stop, it will just continue infinitely. Right? None of these people's derivative becomes a constant or a 0. Derivative of 1 upon z will be minus 1 upon z square. And it will continue, it will become 1 upon z cube, 1 upon z raised to 4 and so on. If you continue taking derivatives. Same thing will happen for the other fellow. So integration by parts won't work here. Integration by parts works only when one of your terms over there is a polynomial. These are not polynomials. Or you have something nice functions, a nice combination, like e raised to ax into sine of bx, and those are nice people, in nice combinations rather. Here what you'll do, what is the technique here? When you get stuck in solving these problems at this stage, man, I don't know anything like this. Everyone heard of partial fractions? Can you use partial fractions here? Yeah, no. If you use partial fractions, you can integrate. No, see, do you all know the integral of this fellow? Yes, it is log of z. Integral of this fellow is log of z plus 1. Okay, so you all know both the integrals. So if I can write this product as a sum, then you are done. No? But what will be the partial fraction here? Which bracket? How do you do partial fractions? You write it as a upon z plus b upon z plus 1. Okay? Then you will cross multiply and you will know the remaining part. No, I am become an expert in this. I can look at this and tell you what is a and b over here. What is a and b anyways? Yeah, a is 1 and b is minus 1. Okay. Otherwise, if you can't look and tell, you will have to simplify this. Anyways, I'll show you all the simplification method. Only after you become experts, then you all can do that. It's a very dangerous shortcut also anyways. Yeah, so how do you all deal with this situation now? You all multiply this denominators on top, right? So only one will remain here. So become a times z z into z plus 1, and here will become b z into, this is z and this is z plus 1. Okay, so z will cancel, you will get a times z plus 1 here, and you will get b times z. What you do next, you collect the terms, which are of the same, collect the terms with the same coefficients rather. So a b times z plus a, this is 1. Okay, what do we do next? Next, what do you do? You compare the degrees, right? So you compare the degrees over here. What is the degree 0 term on this side? Let's write it like this. Degree 0. So on the LHS, who is the degree 0 term? On the LHS, degree 0 term is this fellow, right? 1. RHS, who is there for degree 0? A, right? Okay, degree 1 who is there on the LHS? Is there any degree 1 term here on the LHS? No, right? So it will become 0 here. Okay, and the RHS who is there? It is A plus B. Don't write it Z, just write the coefficient. Right? So what should be the result you all know? RHS should be equal to LHS terms, right? So this will mean that A is equal to 1, and this will mean that A plus B is equal to 0. So what is A? A is 1. What is B? Minus 1, no? Okay, this is what I told you all. No? Okay, so if you all solve a lot of problems like this, you can do this in your mind only. Okay, by just looking at the problem, you can do the calculations in your mind and get this answer. Otherwise, you'll have to waste your 5 minutes in doing this. Okay, so practice a lot of problems from your 12th standard books and all. Okay, there are no marks and all for this one, by the way, in this course. Okay, I'm supposed to give you all only marks for the answer. So if I'll make a mess over here, no, you will lose all your marks for that and you won't get marks for anything. Okay, so the shorter cut you can use, the better it is. If you'll do all this work and show me, I can't give you any marks for this. That's what I'm saying. Okay, so try to be as short as possible and as accurate also. Yeah, so what is the thing I had? I had the differential equation here. Dz z upon z plus 1 is equal to dx by x, right? So integrating both sides, this should become simplified to 1 upon z minus 1 upon z plus 1. Okay, b is minus 1, a is 1. That's what I've done. By the way, how do I do it directly? No, just cross multiply these things and see you get back the same question. Okay, so you cross multiply over here, z over here, and this z plus 1 goes up here, z goes here, and the product over here in the denominator. Okay, so the numerator cancels out and gives you only 1. Okay, so if you learn this trick now, you can do it directly by cross multiplication. Okay, so dx by x. When you are studying differential equation to know this partial fractions becomes a very important thing over there. So it's better you study now this when you are doing this course. Right, so anyways, 1 upon z plus 1 gives you this. So integrating now, this will become log of z minus log of z plus 1. Okay, and this is going to be ln of x plus, I'll write ln of c here. If everything is in terms of log, I'll write the constant also as log. Okay, so this will become, yeah, log of a minus log of b becomes a upon b. So this will become log of z upon z plus 1 is equal to ln of x into c. Okay, so you can take exponential on both sides. So this will leave you with only this leaves you with z upon z plus 1 is equal to x times c. Okay, so you can write here that you have y by x upon y by x plus 1 is equal to x times c. Right? You can cross multiply this x here on top. You make it y plus x divided by x, and that x and x will cancel over here. Okay, so this will leave you with the final answer as y upon y plus x is equal to x times c. This is your final answer. Okay, clear? So, one more problem will do, and then we'll stop. So here we are, that x times sine of y by x and dy by dx is equal to y times sine of plus x. Okay, so solution. Convert this differential equation in that form which we require. Sine of y by x dy is equal to y by y times sine of y by x plus x dx. So now you'll have to manually verify this. So what is your mxy? Mxy is y times sine of there will be a minus sign, but that's irrelevant to our problem. You'll have to take this term on this side up. You'll get a minus sign there, but we are not so concerned about it. Sine of y by x plus x. Okay, and n of xy is x times sine of y by x so I want to verify whether these functions are homogeneous or not. Okay, so what is going to be m of tx ty? It's going to become minus ty sine of ty upon tx, right, plus tx. Okay, this t and this t will cancel over here inside the sign only, right? Okay, this t and this t will come out common, so you'll get t times minus y times sine of y by x plus x. So this is basically t times m of xy. Okay, so this is homogeneous of degree 1. Okay, so m is a Homogeneous of degree 1. nxy, oh sorry, n of px dy I have to do now. Px dy, so this will give me px times sine of py px. So t will come out common there. I have x sine of y by x. This is nothing but my original function again. This t cancelled here now. So t times n of x. Okay, so we have to manually check this out. It's not so easy to just do it in our minds. Okay, so both are n is also homogeneous of degree 1. Okay, so this is a homogeneous differential. So homogeneous differential equation. Okay. So what we do? Just copy our page got over. Okay, so this is a homogeneous differential equation. So it's got over that side also. Okay. So what do we have here? So put y by x is equal to c. Okay, so this implies that y is equal to xc. So this will leave you with dy by dx is equal to z plus x times dz by dx. Okay. So what is the given differential equation for us? Oh, we have to convert it in a form. Okay. So we are given x times sine of y by x or dy by dx, y times sine of y by x plus x. So what I'll do, I'll divide both sides by this term. This will become dy by dx. Okay, so this will become y sine of okay, so dy by dx is equal to y by x plus 1 upon sine of y by x. Okay, so do the substitution now. So this becomes z plus dy plus x times dz by dx. Okay, this becomes z plus 1 upon sine z. Okay, what will happen next? Z and z will cancel, so you are left out with x dz dx is equal to 1 upon sine z. sin z times dz is equal to dx by x. Integrating both sides, this will leave us with integral of sin is minus cos, right? Minus cos of z is equal to ln of modulus of x plus ln of c. Okay, so ln of x, this will become minus cos, resubstituting what will get? Minus cos of y by x. Okay, so this is your final answer. So I think so I'll have to stop here because there's some meeting in this class. So stop here now. Okay, so we have covered every possible basic homogeneous differential equation. There are a couple more of them. Okay, so I'll give you some of them. You can copy and take them for your homework. Okay, just note them down for your homework. X square minus 2y square is the problem, sir. 1 x square minus 2y square dx plus xy dy, okay, 2 x square y prime minus 3xy minus 2y square is equal to 0, and this should be equal to 0. So next 3 x y prime y plus 2 x e raised to y by x e raised to minus y by x. So on your substitution, this will become e raised to minus z. Okay, next fourth one, x cube plus y cube dx minus xy square. Okay. This is equal to 0. Okay, so try these 4 problems for your homework. So tomorrow we'll study one special case of this, what do you call that? So tomorrow we'll study one special case of this. Special case of this homogeneous differential equations. So for this I'll try to solve in the meantime. If there's any difficulty in this, we'll solve it tomorrow in class. Okay, so tomorrow we'll go to some special variety of this. Okay, so that's all in today. Stop here.